Assalamu alaikum and good afternoon. Today we are going to start a new topic, which is the last topic for our course SKE 4633, which is Synchronous Machines. Synchronous machines is also classified as AC machines, which is similar to induction machines, which means that it is operated based on AC voltage supply. It can be either single phase or three phase, but for our course we will be just focusing on the three phase type. The synchronous machines can be operated as either a motor or as a generator, and we will look both operations in this course. Unlike the induction machines, the steady state speed of the synchronous machines is always at synchronous speed. This is different from the induction machines. If you remember that the steady state speed of the rotor is always less than the synchronous speed. There will be 3 slides or 3 presentations for this topic. The first presentation is going to be on the basic principles of machines, which includes the constructions and the basic principle of operation. The second presentation will be on the equivalent circuits and phasor diagrams of the synchronous machines, and the last presentation is going to be on the power and torque characteristics of the synchronous machines. Let's begin with the basic principles of the synchronous machines. The synchronous machines is a doubly excited machines, which means that both the stator windings, which is called the armature windings, and the rotor windings, which is called the field windings, are excited. The field winding is always excited with a DC current, and if the machine is operated as a generator, then the voltage generated at the stator terminals will be in the form of AC voltage. If the machine is operated as a motor, then the supply to the stator windings, which is the armature winding, is the AC voltage. For example, if the machine is operated as a generator, then we will have a prime mover that will rotate the rotor, and the voltage produced or the voltage generated at the stator terminals will be the three-phase voltage. The rotor is excited through the slip rings by the DC current. In terms of rotor constructions, the synchronous machines can be divided into 2 types: salient pole rotors. The winding on the stator, which is the armature of the machine, is similar to the windings of the stator for the induction machines. However, as shown in this figure here, the structure of the rotor is non-cylindrical. In other words, the air gap is not constant or not uniform. The rotor has a salient pole and it is excited by a DC current IF. This is the magnetic axis of phase A, and this is the magnetic axis of the rotor. When the field winding is excited, then the rotor becomes an electromagnet, which rotates around the stator. Now, this type of machines, which is the salient pole rotors, normally operates at low speed. Typically, it has a large number of poles, can be as high as 50, and a good example would be the applications in the hydroelectric power station. This is an example of a salient pole rotors under construction. These are the faces of the salient poles and their respective windings. The second type of rotor construction is what we call the cylindrical rotors. In the cylindrical rotors, the air gap is uniform. This is the magnetic axis of phase A, and this is the magnetic axis of the rotor. The windings on the rotor is normally distributed. When the rotor is excited with a DC current and it is rotating, then we have an electromagnet which is rotating around the stator. Typically, the cylindrical rotors synchronous machines operates at relatively higher speed compared to the salient pole rotors. It has a relatively smaller number of poles, and a good example would be the applications in the steam turbines power stations where the rotation is very high. This is an example of a picture of the rotor with cylindrical structure. This is another example of a salient rotor. This picture shows the stator which is under construction. You can see the size of the machine, which is quite large. This is another example of the picture of a non-salient pole, which is a cylindrical rotor type synchronous machine. Let's focus on the synchronous generators now. This is a simplified diagram of a salient pole synchronous generator. If the field is excited with a DC current, then due to the shape of the pole face, a sinusoidal flux will be produced in the air gap. And since the rotor is rotating, this sinusoidal flux will be rotating in the air gap. The sinusoidal flux which is rotating will induce voltage on the stator windings A, B and C. Because of the sinusoidal flux distribution in the air gap, then the produced or the induced voltage on the stator is also going to be sinusoidal. Since the separation between the windings of A, B and C is 120 electrical degrees, then the phase difference between the induced voltage on the stator will be at 120 degrees as well. Similar to the induction machines, the RMS induced voltage per phase is given by this equation here. The expression is derived from the Faraday's law, which states that the induced EMF is equals to the rate of change of the flux linkage. F is the frequency of the induced voltage, phi is the flux per pole, N is the number of turns per pole, and Kw is the winding factor. The winding factor Kw is to represent the reductions in the induced voltage due to the distributed windings on the stator. This induced voltage is also known as the excitation voltage. The frequency of the induced voltage, or the excitation voltage, can be obtained by using the same expressions that we use for the induction machine, where N is the speed in rotation per minute and P is the number of poles. If the RMS of the induced voltage is plotted as a function of the field current, IF, then we will get what we call the magnetization characteristic curve of the synchronous machine, which is shown here. If you remember, the shape is almost similar to the shapes of the magnetization curve that we used for the DC machine previously. As the field current is increased, the flux in the core saturated, and since EF is proportional to the flux, then the saturation will also be reflected in this magnetization curve. Synchronous generators are widely used in power system applications. They are used to convert the mechanical energy, which is provided by the prime mover, to the electrical energy. The source of energy for the prime movers are coming from various sources, such as hydroelectric, steam, nuclear or thermal. The voltage generated by the generators is then stepped up before it is connected to the transmission line. Transmission lines normally operate at high voltages in order to reduce the copper losses in the transmission line. The voltage is then stepped down before it is distributed to the users. This is another illustration of a grid system. Here we have several synchronous generators connected in parallel to the grid system. If huge number of synchronous generators are connected in parallel to the grid or a bus, then that grid or bus becomes an infinite bus. So what is an infinite bus? It is a point of common connections of the parallel connected generators, for example a transmission line, in which the magnitude of its voltage and its frequency remain the same regardless of the load variations. For example, if we connect a synchronous generator to an infinite bus, then if we vary the mechanical power of the prime mover of the synchronous generator, the steady state frequency, hence the speed of the generator, will remain the same at the bus frequency. We will look at this in detail later on. In fact, in all the examples as well as questions in the exam and in the test for this course, the synchronous generator or motor is always assumed to be connected to the infinite bus. When the machine is connected as a motor, we supply the stator terminals with three-phase power supply. And we have seen earlier in the induction motor that when we do this, when we supply the three-phase power supply to the three-phase windings on the stator, we will produce a rotating magnetic flux. The rotating magnetic flux is similar of having a north and south pole of a magnet rotating at a speed of, say, 3600 rpm as shown here. When we excite the rotor, then the rotor will become an electromagnet with its own north and south pole, which is shown here. Because of the rotor which have its inertia, it will not be able to follow this fast rotating flux. The rotor will not be able to start rotating, or the synchronous motor will not be able to start if we directly connect this three-phase supply to the stator. So how do we solve the problem of starting the synchronous motor? There are two ways to do that. The first one is to use a variable frequency supply. In this way, we slowly vary the frequency applied to the synchronous motor through the frequency converter or the power electronic converters. If the frequency of the rotating air gap varies slowly or increase slowly, then the rotor should be able to catch up with this rotating air gap flux. However, this method requires an expensive frequency converter, which is a power electronics converter. The second method is to use what we call the damper winding. A damper winding consists of bars which are embedded into the surface of the stator pole. The starting characteristics of this synchronous motor with damper winding is going to be exactly the same as the starting characteristics of an induction motor. Once the synchronous speed is reached, then the bars will not be affecting the dynamics of the synchronous motor because there will be no current or voltage induced in the bar.